Our map of the solar system is a human invention. We observe the bodies around us, we categorize them, and as our instruments capture sharper data, those categories inevitably shift. The celestial taxonomy is a fluid process. On January 1st, 1801, astronomer Giuseppe Piazzi discovered a massive object orbiting between Mars and Jupiter. It was immediately hailed as a brand new planet, but that label didn't last. As telescopes found dozens of other objects in the exact same orbital neighborhood, it was downgraded to an asteroid. Today, we know it as Ceres. Over a century later, in 1930, astronomer Clyde Tombaugh triggered a nearly identical taxonomic event. He located what the scientific community eagerly accepted as the solar system's ninth major planet. The observation pushed the boundaries again. In 2006, the International Astronomical Union held a formal vote that officially stripped Pluto of its major planet status. This was not an arbitrary demotion. The creation of the dwarf planet category was a necessary structural adjustment to address a complex class of celestial bodies that broke the existing rules of planetary science. Currently, the IAU, or the International Astronomical Union, recognizes exactly 5 members in this distinct category: Eris, Pluto, Haumea, Makemake, and Eris. These bodies span vast distances across the solar system, from the relatively close inner asteroid belt out into the deep frozen expanse of the Kuiper Belt. So how do such disparate worlds share unified classification? To answer that, we have to discard the assumption that the word dwarf implies these are inert, monolithic rocks. By cross-examining their physical metrics, systemic diversity, and extreme environments, we can decode the precise parameters that define this astronomical class. To understand these worlds, we must build a comparative data model, starting with the physical baselines of scale and location. We establish our starting baseline with Ceres, the absolute smallest recognized member of the group. It holds a unique geographic location as the sole dwarf planet situated in the inner solar system, while at the bottom of the dwarf size chart, it commands a dominant presence as the largest body in the asteroid belt, spinning through 9-hour days. But if we shift focus to the far outer solar system, the data model gets more complicated. In 2005, a team led by Michael D. Brown discovered Eris. Eris presents a stark visual profile. It is an icy, heavily shadowed world accompanied by a single known moon, Dysnomia. Eris introduces a profound density paradox. Look at their volume. Pluto is physically larger, yet tipped the scale to measure density, and Eris packs in more matter, making it the most massive dwarf planet in the solar system. Size alone does not dictate gravitational impact though. This class features extreme variations in mass to volume ratios that actively challenge standard planetary assumptions. Beyond their physical makeup, dwarf planets exhibit highly complex orbital structures. Consider Pluto's extensive satellite system. It controls 5 known moons: Nix, Hydra, Kerberos, Styx, and its largest companion, Charon. In the standard planetary model, a small moon orbits the precise gravitational center of its host. Pluto breaks this standard dynamic. Charon is so massive relative to Pluto that the gravitational anchor is pulled off-center. Instead of Charon circling a stationary Pluto, they orbit a shared barycenter, an invisible point in space exactly between them. These worlds anchor highly evolved binary gravitational systems, exercising a level of structural influence once thought reserved for major planets. Moving deeper into the outer Kuiper belt, we encounter severe morphological anomalies. Take Haumea, discovered in 2004, identifiable by its distinct oval shape and 2 moons, Hiaka and Namaka. Its surface is highly reflective, covered almost entirely by a crust of crystalline water ice. Then, an observational breakthrough in 2017 revealed that Haumea actually harbors a planetary ring system. This makes Haumea the first known dwarf planet to possess a ring, a structural feature previously associated strictly with the massive gas giants. To evaluate the extreme environmental limits of this planetary class, we look to Makemake, discovered in 2005. Measuring roughly 1,430 kilometers in diameter, Makemake experiences severe environmental drops. with surface temperatures plunging to near 400 degrees below zero. This deep freeze is consistent across the outer belt. Thermal readings of both Eris and Pluto plunged below minus 230 degrees Celsius, making them some of the coldest known worlds in the solar system. These bodies endure the most hostile thermal environments imaginable. Yet, they still maintain active, complex geology and advanced structural features. The accumulated evidence rejects the premise that dwarf is just a mere size classification. We've measured profound density paradoxes, where a smaller body like Eris outmasses the larger Pluto. We've mapped systemic complexities that include multi-moon satellites and off-center barycentric orbits, and we've observed morphological diversity, ranging from pure water ice albedos to unexpected planetary rings. The dwarf planet is a robust, dynamic astronomical class of its own, characterized by extreme physical diversity. The 2006 IAU ruling successfully grouped these distinct worlds into a coherent scientific model. This class effectively bridges the structural gap between the chaotic debris of the main asteroid belt and the massive, cleared orbital paths of the major planets. The recognized dwarfs are Ceres, Pluto, Haumea, Makemake, and Eris. As our observational reach deepens, the taxonomy of our solar system will continue to evolve, driven entirely by the complex physical realities of these distant worlds. Thank you for watching.